I would like to introduce our first speaker, Rena Hayashi, with the presentation titled Viruses Evolve, ウイルスは進化する. Take it away.
Okay. Thank you for kind introduction. Today, I would like to talk about virus. Virus is in ウイルス in Japanese. What comes to mind when you hear the word virus? Influenza or Yeah, exactly. Yeah. Is it COVID-19? Today, I will talk about the emergence of different types of virus. Okay. Before I begin, let me briefly introduce myself. My name is Rena Hayashi. I'm a second-year master's student of Kyushu University. My major is mathematical biology. It is 数理生物学 in Japanese, math and biology. And then biology is ウイルス学 in Japanese. And statistics is 統計学. Yeah, my major is and so on. And I like programming and Disney and Pokemon trading card. Today's t-shirt is also Pokemon t-shirts. That is Hogerta. Yeah, and then on the left you can see a photo of me. That is during the Pokemon card tournament where I transmitted to being featured on YouTube live stream. Yeah, in Niigata. I will be delighted to answer any question related to Pokemon card or Pokemon. Yeah, Pokemon card or Pokemon as well. Anyway, the main message for today is that viruses evolve. As you see in the case of COVID-19, we have witnessed the emergence of numerous variants such as the alpha strain or beta strain, Omicron variants, as you hear. Yeah? The transition between these variants represents the evolution of the viruses. Today I will discuss the mechanism behind this evolution. First, I will explain how virus enter cells using the alpha strain as an example. The alpha strain has a mutation called N501Y in the spike. The spike consists about 1,300 amino acids, and in the case of N501Y, the 501st amino acid was replaced. Oops. Sorry. Yeah. So, in the case, the 501st amino acid was replaced with Y from the N. Y is the tyrosine, and N is asparagine. That is the name. From epidemiological analysis, it is believed that this mutation, this change, increased the infectivity. A spike protein binds to spike protein and cells and binds to cells and enter the cells. Will enter the cells. Unlike bacteria, viruses cannot multiply or cannot increase on their own. So, they invite the cells of other organisms, such as human or other animals, and then multiply by causing them to make copies of themselves, make copies, and they increase. Then, at this time, a large number 1 million or so, a large number of viral genes are copied. In the case of new coronavirus, as it repeats copying many times, a very small mistake occurs in the sequence of a substance called RNA, which is responsible for genetic information. This copy mistake, so-called changed in genetic information, is called mutation. Mutation is also copy mistake of RNA. The virus gradually mutates as it spreads from person to person. This mutated virus is a mutant strain, new virus, or new strain alpha or beta strain. Even small mutations in important parts of the viral genetic code can change the nature of the virus. What these mutant strains have in common is that there is a mutation in the genetic information of the spike protein part of the virus. So, spike protein's properties may change, that is the new virus, and these are three issues. This mutation has three issues. One is increased ease of spread of infection. That is they get high infectivity. Then second is severity of the diseases caused, that is heavy symptoms, that is cause heavy symptoms. The third, that is escape immunity. This mutation caused the new viral strain. That is from newspaper in South Africa. That is very new strain emerged and replaced new strain and emerged and disappeared and the new strain emerged. That is previously beta strain or delta strain were prevalent. Then mutations different from the previous type may emerge and spread and replace old strain. After infecting the host, the viral strain produces mutants by mistake of replication. Even if the mutant strain has a higher rate of population growth from the previous strain or wild type strain, the new mutant often goes extinct due to stochasticity. Almost mutants disappear, but because a novel mutant must start from a single infected cell, and number of cells infected by mutant strain is small in the initial period, they experience extinction due to the stochasticity caused by the smallness of the number of cells. I ask, what is the probability of mutations that escape stochastic extinction and they survive in the early stage of infection? I also ask, when are drug resistance mutations more likely to appear? These two questions can be answered by using using math. sorry. Yeah. Yeah. I solve these problems using math. Virus proliferation is often modeled in terms of free viral particles, that is a problem. An infected cell rupture and produce many viral particles, that is viruses, and some of them infect on the cells successfully. For some virus, the infection by cell-to-cell contact is known to be important. Here are infected cells, and that is normal cells. Then they encounter target normal cells and make it infected, that is become infected cell. I explain the cell-to-cell contact infection today. That is really much, but that is OD. We call ODE. We first calculate the differential equation for normal cells and infected cells. That is graph right hand side. Then, using the result of the normal cells, we then calculate the differential equation for the establishment probability. That is this probability. This probability shows that the mutant, how much mutant can survive. That is 100% to 0%. Then that is the time of some people infect, and then the infected is time 0 to we calculate the establishment probability. Okay. Then the time-dependent solution of the number of normal cells is shown. Then it is initially high when the number of normal cells in a wild-type strain is small and the number of normal cells is large. That is first time is very high rate of establishment probability. Then suppose that drug administration. Suppose that a patient takes antiviral drug after the virus increases in abundance in the host. We consider the establishment probability of mutant strain that can escape the drug. We note two different effects of this event. First, the normal type is competitive and will stop proliferation after drug administration, and it decreases in abundance, and the number of target cells recovers. This should improve the growth rate of drug-resistant mutants. Second, the normal type stop proliferation. No new mutants are produced after drug administration. So my question is, when do mutations of drug resistance appear? Likely to appear. Okay. Then using math, I also calculate when the mutant type has a higher infection rate than wild type. By multiplying the number of mutant cells produced and the establishment probability, we can show the number of mutant cells that escape stochastic extinction has a peak at the time of drug administration. There is another peak of established probability, which is the same one as I explained it before. Hence, there are two peaks of establishment probability, that is initial phase and drug administration phase. So I have talked about it a lot, that is using math, but viruses evolve until now, and unfortunately from now on. I would appreciate it if you could have a little interest in the evolution of viruses, starting from copy mistakes. Thank you for your kind attention. Thank you.
Thank you very much. Well, floor is open for questions. So please, whether it be viruses, evolution, and whatnot. Go ahead.
So, well, a little bit different from
Actually, could you sit down? You're going to block that.
Yeah. いや、日本語のみ。
どっちで、日本語のみはちゃんと答える気がしますね。
オミクロンとかいろんなのが起こってますよね。
はい。
で、そのミューテーションがアトランダムに起こったらどうして特定の型っていうふうに集結するんですか。全くです。アトランダムだったら一定のバラバラになるはずだと思うんだけど、ある時点にはある方が出てきて、別の時点には別の方が出てくるという、そういうトレンドがどうやって起こるアトランダムのはずなのか。
Do we need an English translation for that?
Yeah, I need to explain in English.
I think I got it. Yeah.
Well, it's essentially if it's random, why are there like
So if the mutation is at random,
Yeah.
then why certain types of the mutation gathers?
Yeah,
Or,
proliferate.
yeah, Omicron or the Delta or something.
Yeah.
日本語で答えいいですか。正確にお答えすると、名前がついた株がこの3つっていうだけで、変異自体は世界各地とか個々人の体の中でたくさん作られてるんですね。その中でもたまたま感染力が高かったとか、確率的に絶滅することを免れた株がたまたま広がって残ってるに過ぎないっていうのが、今の主流の考え方になります。なので今ベータ株と名前がついているものも実は違う性質を持つものがベータ株と名前がついてもおかしくなかった。アルファベータガンマってギリシャ文字の順番なので出てきた順番に名前がついてるだけで、別にその株がベータ株と呼ばれるわけではないっていうのが回答になるかと思います。
Do you have to translate?
Do you want an English version of that, or do we
So
keep that?
mutations are occurring at random. So there are a lot of different types of
Actually,
mutations.
maybe she should just answer.
But certain types were strong in terms of infection and remaining in your body. So, well, there must be a lot of different types, but on the surface, this type appears stronger.
Yeah. So basically, there's more mutations
Yeah,
than
more
names.
mutation.
Okay.
So
Is that a succinct description? There's just more mutations occurring than we actually give names to.
Yeah,
Okay,
yeah.
gotcha.
We only give names to the ones that take.
Yeah,
Yeah.
we give names to
Yeah.
that stay.
Yeah.
The
Gotcha.
dominant
Yeah.
ones. Too many to name.
Within a name.
Questions? I did have a question regarding the drug administration part. That's considering like if there's drug administration, does that also take in consideration like people already infected, develop immunity, or have been vaccinated, or this is just for like, or is what kind of parameters do you look at when it comes to drug administration? Just straight like 投与して、すでになんかワクチンにつけてるとか、そういうことは入るんですか？
これ、I don't include the vaccination, the effect of vaccination for this calculation, but if I include the effect in this calculation, maybe this peak also emerged, I thought. So that is when initial phase and the acclimation phase is more easy to appear, mutations is more easy to appear, I think.
Like, look, if nobody's gonna be happy, please ask questions because I'm gonna keep asking. In this case, is the coronavirus is COVID-19 more susceptible to develop mutation? To develop mutation, and that's why we have so many variants, and then it was so infectious, or is that just like a general quality of viruses in general, and that like it was since COVID had such severe reactions to people because of that case?
So I think that is people in 2020 people doesn't have the immunity for COVID-19, so and then COVID-19 really spread and the virus get chance to make many viruses, so that is really spread and that is spread, I think. Is it 回答になってますか？ Can I answer? Yeah.
Yeah, okay.
Oh, wait, sorry.
I had a very simple question. So you talked about the copying and mistakes in copying. How often, what probability does that happen? Is it sort of 1 in 100, 1 in a million? What kind of level are we talking about?
Really just 1%, but copies are 1 million or 1 million times, so that is very 100 times mutation appears, so that is really 1% or so.
Thank you.
Sorry, we'll go in and no, you first.
Can I speak Japanese?
This is a bilingual.
人が進化するっていうことは、刺激があってそれに対する反応とか乗り越えるためのもので進化してきましたので、もうウイルスがこうに変容していくっていうことが全てパスビリティの影響だとすると、最初ウイルスってなんか強くなって弱くなってきますね。それが説明できないじゃないですか。どんどん強いものが生き残るっていう可能性が強いのに、なんで同じパターンで強い反応下がってます。その理由はどういう説明ですか？
ウイルスはウイルス自身だけじゃ生きれないんですね。人とか他の動物に感染しないと生きられないので、強すぎて感染したホストが死んでしまうと自分自身も死んでしまうことにつながるので、ただ強いだけだとウイルスって実は生き残れないんです。なのでより広く感染できて、なおかつホストに寄生ある意味し続けれるのが強いウイルスの戦略として強いウイルスなので、強いだけだと、人類絶滅して終わってしまったらウイルスも終わってしまうので、それが起こらないっていうことで。
それはだからコロナウイルスとしてはその強いのはなくなるけど、コロナウイルスとしてはもっと広がるわけです。死なないから。コロナウイルスは RNA バイラスです、ね。DNA バイラスだとまた話が違ってくるんですよ。その辺簡単にいいですね。
DNA だと違うんですけれど、最初の図の話でいくと、ここが RNA か DNA かの違いなんですけど、結局スパイクタンパク質って言って、ここで細胞と結合するところのタンパク質をタンパク質の情報を持っている DNA の箇所が変わると結局同じことが起こりますね。あとの違いでいくと、感染としては
ミューテーションの起こりやすさとかは同じなんです。RNA も DNA も。
いや RNA の方が起こりやすいですね。DNA は、自分たちの遺伝情報なので、もうエラーが起きないように大切にシステム上も保護されていると思っていただいて差し支えなくて、 RNA はすごい不安定な一時的なものでずっと状態を維持しているので、不安定な分変化しやすい。でそれが変異の出てくる変異の出現につながるっていうような形になります。はい、おっしゃる通り。Yes.
Yes. You there?
I have a very simple question. So, can we predict like when we might see the next like variants that it's gonna be like dangerous for us? Is there any way? Because you said that we can like predict the probability of the mutation. So, how many mutations we might need to see a variant that is like drug resistant? So, like when we should be afraid of the next?
When's the doomsday clock?
So I calculate just the probability, so that is not the number. So so I very simple answer is I don't know, I can't calculate because I can calculate just the probability, not the number. So yeah, if I observe the number of new mutations, I can calculate the number of mutations which we scared one. But now we can't observe the number of mutant strains, all of them. So we can calculate just probability, I think. Is that?
This has nothing to do with the presentation.
Yeah.
It's about the Pokemon card. Yeah. So why are there like I see people like lining up in front of like Yodobashi camera like, like what is happening with that?
So in Pokemon card games, sometimes very high rarity card is card be sold that is 100,000 yen per 1,000. Just one card is one. Then that is the card includes just 5,000 yen box. So people want to buy, and lucky one can get this high rated card, so they lined.
So it's not about like playing the game.
Yeah, I think so. Yeah, so our player is also annoyed. Yeah, very annoyed. Yeah.
Okay, if we don't have any more questions, please give another round of applause.
Thank you.